Hi guys, this is Novitoll. From now on I will try to upload more videos on YouTube in English due to a variety of reasons. The first and the major reason is that I'm not practicing English anymore. This is really bad for me. Not being abroad due to pandemic and other stuff. So I hope so that by doing that we will be it will be mutually beneficial for both of us. Like for me, in terms of practicing, and for you, probably like as a broader audience, which I'm not targeting to. But yeah, we will see how it goes. So today we will talk about the Vulnserver KSTET commands. This is the last episode of the Vulnserver series. KSTET commands exploitation is very unique. Let's just switch to Kali Linux. It's really unique, and yeah, and by the way, spoiler, that I'm not going to exploit the actual Vulnserver command itself. I'm just going to go over my this is the cherry tree, just my notes and the screenshots that I made, because I've already exploited this Vulnserver I guess a couple of months ago when I was preparing to the OEC. So yeah, I think it will be okay with that. So with the KSTET, what you need to do, first of all, you just start with spiking, the same spike as we did in the last videos with the true and with the Gumon and the other stuff. So KSTET, the same thing. We just overflowing our stack. Our stack, we found out, yeah, we just first exploited we executed spike generic send TCP by this IP address and the TCP ports, check spike script, and on the other side we were debugging our Vulnserver exe file, and it was crashed, and we see that our EBP and the return EIP was overridden by 41 byte. And also our ESP is pointing to the last byte is C8, and C8 is the buffer of 20 bytes that we are actually controlling. So what it means that we have stack buffer overflow, and we control our EIP, and it means that we just need to find the right EIP. So we are doing the return to libc attack, and by good old-fashioned MSF pattern create, we are creating our pattern here. So we created pattern for 5100 bytes. We send it, also doing this prefix generated from the spike, and we crashed our Vulnserver as well. Our return EIP is overridden with this value. We copied this value, and we are calculated the offset from this pattern, and it turns out that it's 66 bytes. So 66 bytes is enough to control our EIP. We are editing our exploit Python file. So we are sending 66 A's and 4 B's to overwrite EIP, and after that we're just checking if we can control more bytes, like after overflow, because here we saw that we control like 20 bytes, but what about if we send after EIP 40 bytes? We send it, the Vulnserver crashed it with 42 on the EIP, but instead of 40 bytes we see that our stack pointer is pointing to the 20 bytes, so we have only like half of our payload that we sent here. It means that we need to find the return to libc, the EIP, which does call ESP or jump ESP. Executing the payloads on our stack, because NXBit is disabled. So we found such as modules as in previous videos from essfunc.dll. Here are the addresses, and we can we actually took the first one from the last videos as well, so I guess we will do here as well, yeah, AF. So we put our breakpoint here on the jump ESP, we overflowing, and we can see that when we put the breakpoint here and our debugger grab the breakpoints, our ESP now points to the C8 stack. Here is C8. Yeah, and the C8 is actually, what the hell C8 is? Oh, I see what I did. So yeah, I mean, actually I guess I wanted to do this backwards. So this EB stands for jump, so I wanted to jump backward. Actually it's right, I did it correctly. So we overrided our EIP with this address, and it calls the stack pointer, our stack, and our stack, the first 4 bytes is here. So 2 nubs and jump backwards on the D1. It's actually like jumping backwards, but we cannot like jump too much because, as you can see, our buffer starts from here, like KSTET, and here is our bytes that we're actually sending. So we want to actually jump probably not like a D1, but somewhere here. Let's see what we got here. Yeah, so now I'm trying to do the egghunter. I don't think that I've explained what egghunter is in the previous videos, but in short, this is the special payloads for the like a 32 bytes. Egghunter is, I guess it was first originated for the 32 bits systems, and for the 64 bits it's I guess like 60 bytes, something like that. You can check on the Coriolan page, but the basic idea of the egghunter is scans over one page, which is basically it is in hex and equal to the decimal, like a 4 kilobytes. So it basically scans over some syscall. Yes, syscall number is 29 for the Windows 10, and I guess this is the name of the syscall, anti-access check and audit alarm. So we actually like passing in our payload this number, and it's when we execute this number, we actually like increment this number. Execute this number actually. I don't know how to trigger the syscall, but I guess usually you do that. You do actually something like that. That's what I saw in the shellcodes. But probably if you just go over the egghunter, you will see how you execute syscall from NT systems. So yeah, in the Windows Server 2012 it was changed to 26 in hex. We pass. Yeah, so again, how egghunter works. You use some syscall number to trigger the syscall actually, and this what syscall does, it scans over entire page for a specific tag, and the tag is the custom one. Here I use it the popular VOOT tag. This VOO is not O, which is the 00, and in Mono you can also generate the egghunter by doing these commands, and 64 means for 64 bit system. The binary itself is 32 bytes, but my Windows 10 VM is 64. And yes, you're doing the Win version 10 -T for tag, and you're doing the VOOT, and you can see it's like 50 bytes. Yeah, and it's not enough because our payloads, our buffer is 20 bytes here. So I'm not sure why I actually proceeded with the egghunter, but I tried to do something with the egghunter. So I tried to, this is the how 50 bytes of the egghunter looks like. The here you can see I am pushing to the stack 29, and after that I'm like calling my pointer on the fast segments, and I guess somewhere here you just this is probably actually how I doing, how I'm checking whether the page is valid or not. And after that you doing these instructions like scan, and as you can see I'm doing this twice. Not me, it's like it's how the egghunter works, because you're not pushing only one, where is that, only one tag. It is like 4 bytes, and you're pushing like you want to make sure that your address looks like this as well. So it's like you should see the, oops, how I did that. Anyway, so the idea is that like you will see in your stack like two wood tags. So that's why here in the hunter you will see like a two scanning and looping here. So if it finds the address, it will put to the EDI, and then you jump to the EDI here, because your EDI will point to the beginning of your tag. Here I guess I aligned my stack. I mean, this is not important because this actually didn't work. I'm just like, it was my attempt to use egghunter in this exploitation when we have 20 bytes buffer. What I actually want to do, oh yeah, now I remember. What I actually want to do is that I want to combine egghunter with the another command. So I'm sending KSTET, and I'm also sending like kind of gmon commands where you also can overflow the buffer, and you have some bigger buffer for your payloads. So, and I think that there is in the internet you can find such as exploitation technique where you combine KSTET with the other commands of Vulnserver, and in KSTET you use egghunter, and in another payload you will use gmon only to place their buffer, and in KSTET you will kind of search for your buffer. So this is how it actually does. I hope this is understandable. If not, let me actually do the following. Let me go to this paints, my beautiful paints, and let me just try to explain very briefly what I want to do. So here I'm sending my KSTET, and I want to make sure this is not big fonts like for the title, just a simple KSTET, and here I'm just sending my gmon. And KSTET, you are placing your egghunter, and gmon, you are placing your payloads. And what egghunter does, like as I say, it's like because this gmon also, like, you know, is placed somewhere in the process. This is the one process, and it's like kind of stack. And what egghunter does is like scans one page for like 4 kilobytes of address memory, and here in the payload you add your tag like a voot plus, actually like a voot, and it's also need to make sure it's in the little endian. It means that this string will be reversed, so plus your payload. So when the egghunter scans the page, it finds the address of this voot, and as you could see in the shellcodes of the egghunter, it jumps to the ADI where it places the address of this voot, and then it jumps here and executes your payload. This is how it was the strategy first initially, but it didn't work out, I guess, due to that this is possible. In internet, the public solutions for this like a problem, there was like, they made it on Windows 7 or some old Windows version, and I'm using Windows 10, and for me it didn't work out. I probably needed to switch my egghunter to like 64-bit version, but as I say, it didn't work out. Here, as you can see, I found only one tag, so I made my egghunter, and now my EDI points to the next address after my voot. So this is actually voot, as you can see, the hex bytes, but there is no second tag, and it means that the next commands will actually fail. So yeah, I made some note that it didn't work. So what I want to do next is the socket reuse. Socket reuse technique is very, very useful and crucial, I think, in the terms of exploitation when you have a very narrow buffer. And this is, I will try it. I'm emphasizing on this exploit because this is very useful. So The idea of the socket reuse is that any server which is written like, you know, I mean, basically any server uses some sockets to opens the TCP connection. I mean, it should, like, you know, listen to it. And in sockets, I mean, the Vulnserver uses the sockets, and in the sockets there is actually like two commands. So socket receive and socket send. In the receive, you actually like receiving incoming bytes, and in send, you, like, you know, it's outgoing, it's outbound. You are sending to me, to my host, I mean to clients. So the idea of the socket reuse exploitation is the following: you need to find the address of the receive function, because it's already placed in somewhere in stack. You found it, and if you will go through to the manual page of the receive, especially for this from the Windows, let me see, I'm not sure if it is this one, but yeah, I guess this should be okay. So the receive function is basically simple. It is the it has integer to return. It has 4 parameters. Remember that in 32-bit systems we pass our parameters in stack, and the first parameter is the socket object. Then you have the pointer for the buffer char, and you have your length that you want to place, and flags. For the flags we made it, I guess, zeros. And here you can see the description per each field. And this is, like, as I say, it's parameters passed via stack. So you can see that before calling receive in the software itself, in the Vulnserver, you place first flag, then you place what is the length, where, so flag, length, then buffer, the pointer, and then this the socket as object, and then you call the receive. So if you just put the breakpoint here, and you can see in the stack, it's like it's already I guess it's like the debugger shows you all these functions that's going to be placed. I mean, all these parameters going to be placed in this function. As you can see, it's like it's very nicely described here. So you have the socket, which is actually a file descriptor, because the socket returns a file descriptor, and you have the buffer pointer where receiving bytes will be placed, and you have a buffer size which is 4 kilobytes. This is in hex, and you have flags which is zeros. So yeah, and we just need to make sure that we want to place. So the strategy is following that: you use the same address of the receive, and you put the same in your stack. Your payload will be very short, enough to place these bytes on your stack, on your payload. So you put your first payload will be sending within 20 bytes buffer receive plus these parameters in your stack. Then you're sending actually the second payload. So let me just go to the ends just to make sure you are on the same page how this works. I mean, how will it be in the ends eventually. So this is the socket reuse payloads, and we are sending the KSTET. We are overflowing our buffer. We what else? And for the EIP, we are using the socket reuse, right? Yeah, we're using socket reuse. We are changing our for the what is this? For the EIP, we are using jump ESP as usual, because we want to execute our stack, and we just do the jump back for jumping back to the socket reuse here, and then we just do the socket reuse. This is like, I guess this is for the for the padding, because we are just you know, sending junk bytes here. So after that, we send our first stage payloads where we call the receive here, which is socket. You know, we like triggering receive function to receive more bytes, and for the more bytes, I mean that we will send our sockets, expecting now that we will send more like 124 bytes in hex, which is like 4 kilobytes of payloads. And now we are sending our second stage payloads, and we need just to make sure that it is, I guess here I used my length value as the 400 because it was enough, because my payload size is like 351 bytes, and this is in hex as well. So if you will just churn, I mean if you will do in the decimal, it will be bigger value. So in the second stage payloads, we are sending our actual shellcode with the receive TCP shell, and that's it. Yeah, this is like how actually socket reuse works. Let's just go through quickly over development of RISC-V, of developing the first shellcodes. So like I say, this is the pointer, this is the value that's going to on top of the stack. We found our descriptor, which is here 124, but we found the descriptor where it is here, 00401934. We found our F07 ads. Oh yeah, so this is the where this 124 actually placed it. So as you can see, this is the pointer 70. If we will go to the EBP 70 FF70, no, I'm doing something wrong. Where is the ABP? How it goes there? So you have F70, it will be placed here. I don't know what it means, but the basic idea, like, you just need to like find the way found, like, I mean find all these values on stack and just place them in the right order, in the right place. Here I'm adding to my ESP enough bytes to make sure that I'm placing I'm kind of aligning my stack, so when I will place this value, it will be placed here. And yeah, and after that, just like prepare my shellcodes manually. You can use it, you know, that buffer that you actually sent after your EIP, like, which was like a 20 bytes, and it will be enough to place these opcodes for like a push ESP, because you want to actually like push your, you know, kind of back up your ESP first, and then your pop EAX. This will be FD. It will be like a file descriptor. And then you are like placing to the AX, what it is. Oh yeah, I got it. So what I'm doing here on push ESP and pop EAX, I am placing to my EAX my current stack pointer, so that I can add to this AX for the half of that, the 188 in hex bytes, and it will be pointing, and then it will be pointing to my socket FD address, and then I am aligning my stack again to make sure that I'm placing somewhere in another place, not like here, because I don't want to overwrite my my stack. I want to align my stack now. So where it is, so yeah, I will be placing here. I will place my stack. Wait, 64, and it will be, yeah. So it will point here. Then I am like terminating my EBX to push flags here. It will be 0. Yeah. And after that, I just want to call my buffer. So here I'm just pushing my ESP to the stack. I'm popping it to the EBX register. I'm adding to the ABX register 64 bytes, enough to make sure my ESP is pointing to the right buffer. And I'm just pushing my EBX now. And now I'm just ready to call, I guess. Now I'm ready to call the RISC-V function. And yeah, there is a very cool technique using shift right, because in the RISC-V you can see the first byte is 00, which is terminating null bytes, and in order to bypass that, I'm placing to my EX register the like 3 bytes plus some 90 like 90 nope. But after that I'm like shifting to the right my current EAX register on 8, and now on EAX, as you can see, it's nicely pointing to the receive here. So I mean, this shift to EX, it's real cool. So if we just open the terminal, so you have 0x0 0x425C90, and you're shifting to 08. It will be this value here, plus for sure two zeros will be appended to the beginning. So yeah, this is very very short. You can actually I mean, explaining how I did this shellcode, I guess, will be too much, because you can find such information how you can construct your own socket reuse payloads, and I very kind of you know, I emphasize that this socket reuse is very useful. It's very useful in terms of understanding how you can construct such as payloads, but I'm not sure it's very relevant anymore. But yeah, you can just use it for reusing the same sockets, and I guess the same kind of strategy will be used somewhere in the ROotMe challenge. So you can go to the ROotMe, and I guess you will use the socket reuse somewhere here in the I'm not going to spoiler, but it's going to be somewhere here. So socket reuse is very useful, and you will reapply your knowledge in the ROotMe, one of these challenges as well. Yeah, hopefully you like it, but for me it was very useful. Again, I'm trying to practice more, and I guess further we will do more videos in English. I will be more fluent, and try to reminisce all my English skills as well. So yeah, hope you enjoyed, guys. Take care.